assistant professor from San Jose University. He agreed to conduct some lectures to our students. First two lectures were online via Zoom. Today we have hybrid meeting here on site and via Zoom also to our listeners that attended before his classes. So be careful, understand information, new information for us, for you, for us. And after this class, you can ask Benjamin about this topic, other topics that devoted to distributed systems. Please.
Thank you. Thank you. All right, hold on. Let's see. All right, so I'm Ben Reed from SJSU. How many have been here before? Was it the last session? Oh, okay, a couple. Okay, so we're gonna kind of pick up a little bit from the last session. But I want to review a little bit before we go. If you remember the last class, we talked about, and I do want to say one thing just to start off with. I really wish I could speak Ukrainian. It's really hard. But when I talk and I lecture, even in my classes, I'm very bad with details. So sometimes I'll say kilobytes instead of gigabytes, or I'll say a CPU instead of a GPU. So if something comes out strange and you're not understanding, please just stop and ask, okay? And I can help clarify. So anything new, any terms that you need to define, please, I'm happy to stop and talk about it more, okay? So last time we talked about public key, crypto, and we talked about certificates, how web browsers and SSL use certificates so that when we connect to different websites like Google or Amazon or Microsoft, when we connect that, we know that we're talking to the site that we think we're talking to. And that's using certificates that connect the name of the website to a public key. Okay, so we're going to talk about that a little bit more. We're going to go down a little bit lower. We'll talk a little bit about SSL. We'll talk a little bit about SSH. And then we'll kind of dive deep into double ratchet. Has anybody heard of the double ratchet algorithm? It's the one that's used by WhatsApp. Okay, cool. So it'll be interesting. All right, good. It's an interesting protocol, and we're going to spend some time on it. It's kind of complicated, and we're going to go at it at a high level. So I know I'm not going to be able to explain it all to you today, but I do hope that I'll explain enough of it so that if you're interested and you read the papers about double ratchet, you'll be able to understand them a little bit better. Okay? So we're going to start off by just reviewing Diffie-Hellman again. Okay? Diffie-Hellman is my favorite public key algorithm because it's the only one that I can do from memory. All the rest of them I have to look up. But Diffie-Hellman is really nice. Does anybody remember what we use Diffie-Hellman for? What's the purpose of it? Do you know? Right. Yeah, so Diffie-Hellman allows us to do a key exchange. It allows us to calculate, kind of come up with a shared secret without actually passing that secret over the network. Okay, so that's the key part of Diffie-Hellman. So in Diffie-Hellman, there's two parameters that we start with that is known by everyone. So whenever you use Diffie-Hellman, you pick a base, we're calling this G here, and you need to pick a modulo, which we're calling P. And we call it P because the modulo is prime. Okay, so we pick a large prime modulo, usually 496 bit or 4096 bits. So this is a large P right here. The base, which we'll see in a second, is usually quite small. What we do is, given this base and this modulus that everybody uses, so everybody will use the same one, each user in the system picks a random number. Just any random number between 0 and p minus 1, and that will be their secret, their private key. And then for the public key, they take this base and they raise it to, in Alice's case, she raises it to the G of A power modulo P. Okay? So by doing this modulo, we keep the size of the number from exploding. Because if we have G, and then we have this A, which is going to be a huge number. And so if we just keep raising G to the A power, we'll end up with this massive number. But we do it modulo P, so we keep it around however many bits P is. Okay? And then what happens, they exchange GA and GB, and then the shared secret is GAB. They can both calculate GAB. No one else can calculate GAB, because in order to calculate GAB, they would have to know either A or they would have to know B. Or, I mean, in theory, they could take the log of GAB, but that turns out to be very difficult. Okay, so the reason Diffie-Hellman works is because it's very hard to do a discrete log of this value there. Okay, so this gives us a shared secret. This is what we can start working with. So let's see. It worked. So I wanted to give you this. This number isn't important, but for me, when I talk about things, I like to just have an idea of something concrete, just so that in my mind, when I think about it, I have something concrete and I can kind of hold on to that. So this is one of the standard parameters of Diffie-Hellman. It's called, that SSL uses. It's a 496-bit standard. You can look up this information in RFC 7919. Does anybody know what RFC stands for? Request for comments. And what do we use RFCs for? For the what? Yeah. Exactly. Yeah. So RFCs are internet standards, which is kind of funny because the name is request for comment, but that request for comment is a standard. So whenever all the standards, SSL, SSH, TCP, IP, there's an RFC for all of those. And we standardize these, and then developers can develop these algorithms, and they can interoperate. So this has the example parameters for the P and the G used by SSH when you're doing 496. So you'll see that the P is this number right here, right? So it's a 4096-bit number, so it's very large, right? That's a very long number. This is how they calculate it. Here is this calculation right here. This little piece right here, you see, is 2 to the 3,966 times E, which is the natural number. And so this is kind of extracting the first 3,066 bits of the natural number, which is random. Those bits are random. And so that's how they're using it as a random source. So P ends up being this, and our G is 2. It's a nice G to work with, right? 2. We all like base 2 stuff. So G is 2. All right. I can change it. Let me see. All right. So, and this is what we talked about before. we have Amy and Bob here. They're exchanging, they want to come up with a shared secret. So, Amy, when she wants to talk to Bob, she sends G of A. Bob sends G of B, and they can both calculate G of AB, right? Because Amy, when she receives G of B, she has A. A is her secret. So she can do this calculation. And Bob can do the similar calculation, but it receives G of A and it raises it to the bth power. And because this just boils down to multiplication of A and B, and multiplication is commutative, these two calculations result in the same number, and that's the shared secret. Okay? So this is cool. We share a secret. But this only gives us confidentiality. It turns out we don't actually know who we're talking to. Amy doesn't know she's actually talking to Bob. So if you look, we can have a man in the middle attack, right? We'll call it Mal. I didn't want to write out Mallory, but this is the man in the middle. I should have put a black hat on him. All right. So this is the bad guy. So the Mal gets in between Amy and Bob and impersonates each side. Okay. So Bob sends GB to Amy, gets intercepted by Mal, and then Mal sends GM to Amy. So Amy raises GM to the 8th power. And then Amy sends G of A, again, Mal intercepts it, and then Bob raises it G of M to the bth power. So now this shared secret that Amy and Bob feel like they have is not actually there. Bob is sharing a secret with Mal, Amy is sharing a secret with Mal, and then Mal is acting like Amy to Bob and like Bob to Amy. Okay, so it's a literal man in the middle. Totally works, right? That we do Diffie-Hellman. This all works, and it's secret. Like only Amy, Mal, and Bob can see what's going on, but Mal's the bad guy. So that's not good. So we need to fix this, and the problem is we don't have authentication. We have a shared secret, and it is secret, but we don't know who we're sharing it with. So we want to fix it, and we can do that with signatures. Okay, this is signing. So it turns out you can't actually do signatures with Diffie-Hellman, but there is a standard that's very close to it called DSA that allows us to do signatures. The math is a little bit more complicated. We still start with a G and a P, and then we also have a Q. And this Q will be a prime divisor of P minus 1. Okay? Now I'm gonna like say a bunch of math here. We don't have time to cover it at all. Okay? But I just want you to realize that when we talk about signatures and verifying signatures, it involves multiple pieces of information. Okay. When we looked at Diffie-Hellman, it was kind of simple. Amy had an A private key, and G. Whoops. Let me go to the good one. Whoops. Sorry. Here we go. Yeah, and this nice. Amy has A, this private key A, and this public key G of A, and then Bob has B and the public key GB. That's nice and simple. But usually when we work with signatures, it becomes more complicated. We have a lot more information. And even in this case, we have more information because this G is extra things that we need to have to start with. And there's also the mod P, which I'm not representing here. So yeah, so some of the extra information, we have this Q, which is a prime divisor of P minus 1. And the work to find this prime divisor, it is a bit of work, right? We have to do some calculation. Fortunately, we only have to do it once because this Q is a constant that we do with all our calculations. So we can publish this Q along with G and P one time. And then same as before, if Alice wants to assign something, she picks a random K. This will be her public key. And I'm sorry, this will be her private key. And then G to the K will be her public key, which we're calling Y here. Okay, does that make sense so far? All right, and then to sign a message, we do a bunch of math. Okay, so we actually calculate two values. We calculate an R based on this expression here, and we calculate an S. And I just want to point out two kind of interesting things here. When we calculate this S, we use the hash, the digest of a message M. Because when we sign something, we're signing a message. So the input of this is the message and the private key that we're signing that message with, okay? And so we see the message pop up here in the calculation of S. Now the message could be variable size, and it could be very large. If we're sending a video, it's gonna be very, very large, right? And so we never actually sign the message. We sign the digest of the message, which is represented by H. So H is some digest, maybe SHA-256. It would be one very common digest. And then we calculate these two values, and these two values is the signature of M. So here, the signature isn't just one number, it's a two, it's a pair of values. So the output of this signature function is two numbers, R and S. They'll both be of size Q. So they'll be basically half the number of bits of, oh no, not half. They'll be almost the number of bits of P. And then, so when we send the message, we'll send R and S along with the message to indicate that it's been signed by Alice. And then whoever receives that message can verify the signature by calculating these three values, these four values right here. And when they do this last calculation right here, they get this value. And if V equals R, the signature is valid. If it doesn't, then the signature is invalid. So verify just returns a Boolean, whether or not the signature was valid. Okay, there's an interesting, we don't have time to go through it, but if you look at the, I should have written it here, I didn't. So this algorithm is called DSA, Digital Signature Algorithm. And yeah, and so that's this. I want to note one other thing. You'll notice that here we take K is the private key, we take the inverse of the private key. So usually when you take an inverse, you just flip it, right? Because the inverse is what you multiply to get one back. So the inverse of 3 is 1/3, right? But you'll note these are all integer arithmetic. These are all integer values. So we can't represent 1/3 with integer values, okay? But we're doing this modulo Q. So if you look here, here's a quick example for you. If we want to take the inverse of 3 modulo 5, that is actually 2, right? Because if you take 3 and you multiply it by 2, you get 6. And mod 5 will give you 1. Does that make sense? Yeah. So yeah, things work a little bit different when we're talking modular arithmetic. But this kind of thing is used a lot with these algorithms. So this is how we do signatures. Now you'll note when we sign, there's no secrecy. We can sign and we can say, Alice signed this, but we can't make the message private. If we want to make the message private, we need to use Diffie-Hellman. Okay, so we can do the encryption. So we can actually combine these two things together to fix the problem we were talking about before. So before we had Mal trying to get in the middle. So Bob sends this, oh, I think I'm writing, oh, yes. So Bob sends GB to Amy, and then Mal intercepts it. Now, when Mal intercepts it, it needs to send GM to Amy. But now when it sends GM to Amy, Amy's expecting this GM to be signed, right? So it can sign it. It has a private key, Mal. But the problem is when Amy gets it, and you know what? It's getting cut off here. So one of the starting conditions is that Amy has the public key of Bob. So this pub right here that you can't really see is pub of Bob, right? So when Amy gets this signature or gets this message, Amy's going to try and verify the signature with Bob's key, and it will not match because Bob didn't sign it. So Amy will reject this message because she knows it doesn't come from Bob. Okay, now Mal can try a different tactic. So here, Mal tried to like forge this signature, which it can't do because it doesn't have Bob's key. So another thing it can try and do is just tack on the signature and then send its own GM, right? So when it sends its GM over to Amy, Amy's going to look and see if this signature was signed by Bob and the message was GM, but this signature represents a signature over the message GB. So when Amy goes to verify the signature, again, the signature verification will fail because the message that was signed was GB, not GM. Okay, does that make sense? So this is how we can kind of combine these two things together. Any questions? Okay. All right. So it turns out this Diffie-Hellman that I just and the DSA that I just presented is the simple form. Today we use much more advanced. We use elliptic curve crypto, which is you do the same basic operations of DSA and Diffie-Hellman, except instead of working with just straight integers, you map it onto a curve. And that makes all the operations much more complicated, which allows us to use much more shorter keys. Okay, but the ideas are the same. The math just gets way more complicated. All right. So you'll see usually it'll be EC, DH, Diffie-Hellman, and EC DSA. All right. The other concept that we need to talk about is KDFs, key derivation functions. So when we have a secret, oftentimes we want to produce new secrets. And the reason we want to do this is we might start off with a secret that's, I don't know, maybe just 256 bits of secret material. But we want to generate more. We want to generate additional secrets. Maybe we generate a secret between two endpoints, but then we want to generate a secret for sending messages, and we want to generate a secret for receiving messages. And maybe we want to generate another secret for calculating message authentication codes for sending and message authentication codes for receiving. So we want to take that one secret and produce 4 from it. And that's where these key derivation functions come in. They can take a secret and some message and produce a new secret. And that secret might be much larger than the secret that we started with. Okay? These key derivation functions generally use some sort of digest function like SHA-256. Okay? And they kind of mash things together and expand things and result in a bunch of random bits that we use. So the output of these key distribution functions is pseudo-random. Does anybody know why it's not actually random? Why do we call it pseudo-random instead of random? Yeah, exactly. Yeah, exactly. So it looks random. Like to the outside observer, it looks random, and when you test it, you get randomness. However, it's deterministic. If you have the inputs, you get the same output. So you can predict it. right? So it's pseudo-random and not actually random. Okay, and it's also not reversible. This is important. So if you have this secret material output, you can't get back that S, and you can't get back the N. So you can't go backwards. And so we often use this in a chain. We start with the initial secret, and then we'll evolve the secret. So as when we have a secret X, and we get a message that comes in, this will generate a new secret, X plus 1, and some T X plus 1. And then this X plus 1 we'll use for the next key derivation function based on the next message that comes in. But then this T X plus 1 we'll use for something else. Like the app will need to do some encryption or something else. So this will, and we'll see this arise. So this is a very common thing to do with key derivation functions. Okay, so we'll see this in just a sec. Any questions so far? Yeah. Oh, sure. This one. Yeah, so if Mal got B from Bob, this if Mal either got B from Bob or the private key of Bob, either one of those, then then Mal can do bad things. Oh, sorry, did I? Okay, cool. Yeah, so the reason Mal can't get B or the private key of Bob is Bob never puts it on the network. So, yeah. No, no, he still can't unless. So there's supposed to be a priv Bob here, right? If Mal only has B, but doesn't have the private key of Bob, then Mal still can't change this. However, if Mal has B, it can just let this message go by, because if it has B, when it sees the G of A from Amy, it will be able to calculate the shared secret. Mm-hmm. Yeah, so if he sent, so you're saying if he sent G of B to Amy and he signed it with his signature, yeah, then Amy would reject it because she was expecting it to come from Bob. She was expecting it to be signed by Bob, and so she would verify the signature using Bob's public key, and the signature would fail. Yeah, exactly. Yeah, and actually, even that message, if he tried to do that, like if he was able to do that, it really wouldn't help because he doesn't know what B is, and so, yeah. Okay. All right. So let's look at this is from RFC 8446. This is the initial handshake of SSL or TLS. This is what browsers use to do secure channels. And this is, if you look in RFCs, even today, they don't use figures. So they only do ASCII art. Okay, so this is the art inside of RFCs, right? So in TLS, when the client first connects to the server, it sends this hello message, right? So this is the message that the client initially connects and says, hello, server, I want to talk to you. And it sends some information about itself. It sends what algorithms it knows. It sends a couple of random pieces of information to the server. And then the server responds with a hello message. And this hello message has extra information. It has this certificate that it wants to, that that proves that it is who this client is trying to talk to. So for example, if you're connecting to Google, this certificate would have google.com in it. And then it will also have Google's public key. So that when the client then goes to negotiate a secret key with the server, it will have that public key from the certificate to do that negotiation with. Okay, so that's this information that comes down here. And then there's one last handshake here where we finish the calculation of the shared secret. We verify the certificate. SSL, you can also verify the client. So the client can also send a certificate and prove that the client is who it's trying to say it is. Generally, actually, we never use client-side certificates with SSL. So usually with SSL and TLS, so I should just say, the original protocol was called SSL, Secure Socket Layer. When it was standardized in the IETF, the name was changed to TLS. So then the real name, the modern name is TLS, but a lot of people still call it SSL just because we've always called it that. Okay, so the two protocols, technically speaking, are different because SSL is the older version of TLS, but when you see it in practice, the terms are used interchangeably. So when we use SSL and we talk to a server, generally the client knows who it's talking to. When you connect to Google, you know you're talking to Google. But Google doesn't know who the client is using SSL because there's no certificate that comes from the client, right? So this is an asymmetric relationship. The client knows who the server is, but the server doesn't know who the client is. So how does the server find out the identity of the client? You've all done it. You've all done it. When you connect to Google, like when you go to Gmail, how does Gmail know who you are? Okay, how does it get the user ID? Okay, yeah. What's a simpler way to say that? Yeah, but what form does that authentication come in? Like, yeah, what form? How does it look? When Google authenticates you, what does it do? No, but what do you see? What do you see? How does Google know? How does Google learn your user ID? Okay, it does the cookies after it learns your user ID. How does it do it? Okay, this is really simple. Okay, it prompts you, right? When you go to Google, it prompts you and it says, enter your user ID and enter your password, right? So that prompt happens at the application layer. So at the network layer, at TLS layer, it's asymmetric. The client knows who the server is, but the server doesn't know who the client is. So the way the server finds out is it prompts you, right? An HTML form comes up and it says, enter your user ID and password. Now, why is it safe to enter your user ID and password? Because you know you're talking to Google and you know you have a secure channel, so you can just send that user ID and password over. Does that make sense? Yeah? Okay. So this is kind of, in theory, we can authenticate both sides. In practice, this is asymmetric authentication. But it does allow us to have a secure channel, this encrypted channel. So we have confidentiality, but the authentication is asymmetric. Oh no, I need to go faster. All right. So SSL, very similar thing. We have this hello. We have some authentication that happens. In SSH, sometimes it's asymmetric and you get prompted for a password. If you're really cool, you set up authorized keys on each side, and then it's just public key all the way. You don't even get prompted. And they negotiate a master secret. Now, there's a problem with both of these protocols. TLS requires certificates and certificate authorities. SSH doesn't use certificates or certificate authorities, but does require that you distribute the public keys somehow. Usually it's with the first login. You log into the server, it says, hey, I found this public key I've never seen before. Is this right? And you say yes, because how are you going to check, right? So you say yes. But the key thing is, it does establish an end-to-end channel, but in order for this end-to-end channel to be set up, both sides have to be online. They both have to be communicating at the same time. You cannot log into a server that is down using SSH and then go to sleep. And when the server comes up, suddenly it's logged in. That doesn't work, right? So in order for SSL and SSH to work, both servers have to be online because they have to talk to each other. They have to exchange these messages. But sometimes we want end-to-end encryption when both sides might not be running at the same time. Can anybody think of a case where you want end-to-end encryption, but when you actually send the message, one side might not be up? Like the receiver might be down, sender's up, but it wants to send the message, and then maybe when the sender is down, the receiver comes up and it gets the message. Yeah, exactly. So instant messaging, this happens, right? Your friend, you send a WhatsApp message to your friend. Your friend is asleep and his phone ran out of battery, right? You can still send the message and it will be end-to-end encrypted. And then when your friend wakes up, it gets the message, you might be asleep and your phone might be out of battery, but it can still get this end-to-end encrypted message. Kind of cool if you think about it, right? There's none of this handshake that happens. So how does this happen? So the algorithm, it's called double ratchet algorithm. There's a bunch of applications that use it. WhatsApp is the big one. Signal is the kind of original. That's where the work on this algorithm happened. Facebook Messenger uses it. There's others that use it as well. Interesting, Telegram does not use it. But it has these features. Even if the other side is online, end-to-end encryption, it has forward security. Forward security is really cool. You can imagine you have somebody spying on you. And so they collect all your WhatsApp messages, right? And so all the WhatsApp messages you sent for the last 5 years, they've collected it. Now they can't do anything with it because it's encrypted. So they can't read the message, but they've collected it. And meanwhile, they have the supercomputer working to break your public key, right? Because that's how important you are. Nobody would ever do that with my WhatsApp messages. But anyway, so they work out and they finally break the public key and they're like, hey, we broke the public key. And they decrypt a couple of messages. And what do they find? Another public key to break. Okay, that's where this forward security comes in. You break a key, it only gets you a couple of messages and then stops. Some protocols, you break a key and you get everything, right? Everything from then on. Yeah, the details for double ratchet is at this location. I actually use figures from this this document. When we do end-to-end encryption, we don't trust the server. There is a little point where we need the server's help, which we'll point out. But in general, the server doesn't know anything, right? It can see them encryption messages go by, but it doesn't know how to read them, okay? Because it's end-to-end encrypted. So let's see how double ratchet works. First of all, this is the ratchet, okay? The ratchet, yeah. Yeah.
Which are connected with cache. So if you break one book, you can't have access to the previous one. So in the part of, we can read a part of messages, and the previous they have another code.
I don't know, actually. Yeah, I don't know. That's a good question. I don't know enough of the blockchain protocol to answer that. Yeah, that's an interesting question, though. So actually, does everybody know what a ratchet is? Have you used a ratchet before? So the key aspect of a ratchet is when you turn it, it only turns one way. You turn it, and then you can't go backwards because you have this little thing that stops it from going back. So this is what you're supposed to think about. So, like for example, you have, and this ratchet represents a keychain. So you're generating keys out of this ratchet, and it's turning and it's generating these keys, and so this is one ratchet, and then you have another ratchet that feeds into this ratchet. This is where the double ratchet comes in. The ratchet figure doesn't really work for me very much. I just think of key distribution functions, but I guess double key distribution function doesn't sound as cool as double ratchet. So, but basically what we have is a series of Diffie-Hellman keys that get fed into this key distribution function. And this key distribution function will generate new symmetric keys. So these are shared keys that are generated, and then we feed it into ascending key distribution function and a receiving key distribution function. And these will generate receiving and sending keys that the two sides can use to exchange messages. So, for example, we have Alice and Bob. Alice wants to send a message to Bob. And so what Alice does is it gets Bob's public key, and it gets her private key, and it calculates a shared secret. So this is just Diffie-Hellman, right? And this is the output. Okay, so this is the output of the first ratchet, which looks like just Diffie-Hellman. They actually, double ratchet uses an extended version of Diffie-Hellman that works pretty much the same. It just has extra variables that it mixes in, extra information that it mixes in. So at this point, this looks like standard Diffie-Hellman. It's not that interesting. However, this dotted line is kind of suspicious, because one of the big problems in crypto systems is key distribution. And somehow Alice got this public key from Bob, right? So how did that happen, right? So how does that actually happen? So in WhatsApp, you remember when you signed up for WhatsApp, you log in, and then it like sends you say, this is my phone number, and then it sends you this code. And then you type the code into your app, and then it starts working, right? So WhatsApp, the server wants to tie this public key to that phone number. That's what the server does. It keeps track of public keys and the phone numbers they belong to. And so what happens what's happening in your app is you say, I want to register a key for this number. And you send that number up to WhatsApp. WhatsApp is going to send an SMS message to that number. And then, assuming you control that number, you should be able to reproduce that number and send it back up to the server with your phone number and the public key. And when the server receives this information, it will look and say, oh, yeah, this user really does have this phone number because this is the right code. And it will put this phone number and this public key into its database. Does that make sense? Okay. There's more information than this. This is a simplification, but this is the general idea. And then when Alice wants to send the message, she contacts the WhatsApp server and says, hey, I want to talk to this phone number. And the WhatsApp server says, oh, here's the public key for that phone number. Okay, so that's how we did that first step there. Okay, so this public key of Bob came from the server. So this is how we got this output. Now, since Bob has the public key, Bob has its private key, it can put its private key into Diffie-Hellman, and when it gets a message from Alice, so if Alice sends a message to to Bob, she can send a public key to Bob, and they can calculate this shared key secret, this shared public key. Yeah, so this is how they come up with this initial shared secret here. And then when later, when Bob wants to send a new message, it will generate a new public-private key pair, right? Just out of the blue. So this is just a new random one, not registered anywhere. They call these ephemeral public keys. So Bob will generate this public-private key pair, won't store it persistently because it's just temporary. And then we'll send this public key to Alice in a message, and they'll do that exchange. So each time they do an exchange, they're going to generate new public keys. This is where the ratcheting starts. So yeah, so this public key, when Alice sends a message to Bob, she'll include this public key in the message. That will be used for this calculation here, but it will also be used for this calculation here. So when Bob wants to send a new message, it will generate a new public-private key pair. It will calculate a new Diffie-Hellman key, and then it will send this public key to Alice so that she can then generate the public key, the new Diffie-Hellman secret on her side. Okay, is it okay if I do like another 5 minutes? Wait. Yeah, okay. All right, so this is what it looks like. This is what the public key ratchet looks like. So each time when Alice gets a new message from Bob, she's going to generate, Bob will send this public key, a new public key to Alice, and they'll start generating this series of Diffie-Hellman keys. Now, these Diffie-Hellman keys will feed into a chain, a sending chain and a receiving chain. So, yeah, so let me see. So it looks, the receiving chain looks kind of similar. There's this initial chain key that it gets from Diffie-Hellman. So this is the initial key that it gets from Diffie-Hellman. And then it has this constant. I really wanted to look up the constants. Usually they're super boring, like the letter A. Okay, so it's not anything fancy. There's a constant here that we feed in, and this key distribution function will then generate two secrets as output. One secret will be a chain key, which will feed into the next iteration of the key distribution function. So every time we want a new message key from this chain here, we'll simply apply the constant to the last chain key, and we'll get a new message key, right? So this is how we crank out new message keys. And this is the notion of the ratchet. Every time we send a message, we do another iteration of this key distribution function. So this is kind of what it looks like. This is from the paper. Let me go to, this is a more interesting example. So here we have Alice. She wants to send this initial message. So what happens here, she gets the public key from Bob. That's what this part is right here. She has her own public-private key pair. Now this yellow is her using the private key. And then when she sends A1 to Bob, she'll send the public key part of that private key. Okay? So that way, Bob can generate the same secret, generate the same keychain secret for, I'm sorry, I guess on the receiving end. So on Bob's side, this keychain is going to correspond to receiving. So when Alice sends something, she's going to send it using this secret generated on her sending keychain. Bob is going to have a receiving keychain that is generating the same series of secrets, right? And we'll use that keychain to decrypt messages that it gets from Alice. So here we see some messages that are going to come in from, so I think this is from the perspective of Alice. So Alice is generating this A1 message from her sending keychain. Now, when she gets B1, she's going to use her receiving keychain to generate the key for B1 and decrypt the key and decrypt the message B1. Does that make sense? It's a little complicated, right? It's a little, because there's a lot happening. Let me just go back. I think the key thing, so if we rewind a little bit, the key thing is this picture right here. So when I first showed you the picture, it was probably kind of boring. But this is, if you look back, this is the key picture. So when Alice wants to send a message, she wants to generate the initial key for the keychain in her sending keychain. Okay, and she does that by applying Bob's public key and her private key to Diffie-Hellman and getting the shared secret. And that will be the shared secret that will start the sending keychain so that she can send a message. Now, Bob, when it receives that message, it needs to generate the same keychain so it can decrypt the message. So if Alice can generate a keychain and Bob can generate the same keychain, then they'll generate the same shared secrets and they'll be able to decrypt the message that one side sent. So Alice's sending keychain has to produce the same set of secrets that Bob's receiving keychain produces. So they need to be identical keychains. And they are because this sending keychain was produced with the initial public key of Bob and the private key of Alice. So that's how Alice constructed her sending keychain. Bob constructs his sending keychain by using his public key, his private key, and Alice's public key. So this operation right here and this operation right here produces the same number, right? This is GBA and this is GAB, okay? It's going to produce the same number. So these two chains are going to be initialized with that same number, and thus they'll produce the same series of secrets. So when Alice sends a message, she asks for a secret from this keychain here, and when Bob receives the message, Bob will ask the receiving keychain for a secret and decrypt that message. Okay? So, and then the same thing happens on the other side. That's why, if you go back, there's this picture, right? So you have the Diffie-Hellman keychain, where you keep exchanging these public-private keys to generate this sequence of secrets based on Diffie-Hellman. And then those secrets feed into the receiving keychain and the sending keychain. And those are another chain of key derivation functions that will produce secrets. Okay? All right. I know it's a little complicated and it's a little fast. So let me stop there. I highly encourage, if you're at all interested in this, you can read the paper that is here. And again, this is where I got the figures for this lecture. So if you just look for a double ratchet algorithm on Google, this should pop up in one of the first links. Okay. Are there any questions? Yeah.
Group chat.
Oh yeah, with group chat. Right. Yeah, that's a good question. I haven't looked at how they do the group chats, but maybe I don't know. That's a good question.
At the same time, like group has its own shared key, which is its own key, which is shared with other members, and the group like signs.
Maybe, right.
Person that is sent message, the shared key with AG, and if person M sends, when there is something like T⁴ and in my opinion, it take less time, but I actually don't know.
Yeah, I don't know either. I don't know either. I think on that side, I believe they do have, and maybe even in this document and later on, they do talk about it. But I don't know. That's a good question. Yeah. Oh, before this? Oh, like down here?
Yes. As far as I understand, the server controls the amplification in this case.
Ah,
We can say that we have management here, but you didn't show that. And then I think that it was the server, it's the author of the server. Because the public key of the person who did the
yes, good point. So the reason it's not actually the server that prevents the man in the middle. So the server is the one that distributes the key. So the server solves the key distribution problem. Okay, so that's what the server does. The man in the middle is avoided because this public key here is signed by the identity key for Bob. So remember when I said I was like abbreviating the amount of keys that are maintained by the server? So the server, when it sends Alice the public key right here, I simplified it. It's actually a couple of keys that it sends down. It sends down Bob's Diffie-Hellman public key, and it also sends down Bob's DSA public key. And the Diffie-Hellman public key is signed by Bob's DSA public key. So we can verify these signatures. And the other thing I'm skipping over is, and this is super important, the symmetric ratchet chain, this initial secret, this initial secret here is derived from the identity key and the public key. It's derived from a bunch of different pieces of information, but in the end, it's bound to the identity of Bob and Alice. So only Bob and Alice could actually participate in this. But yeah, it's kind of a subtle thing. But that's how you skip the man in the middle. It is actually something they do in the symmetric ratchet chain. Yeah. Yeah, there are a lot of them. There are. So the project we work on actually uses this signal protocol code, and there's a lot of keys, right? And it's actually, and really important in the signal code, they didn't use the same naming conventions as they do in the spec, so it's really hard to map them. But yeah, so there is, let's see if there's a good, I don't have a good list of keys, but so there's one long-lived key, which is called the identity key. So this is the one that is used for signing. So this is a long-lived key that is used for signing. And then there's your initial public key that is used for negotiating the secrets. That one can change periodically. And then they also have some other keys that that are one-time use. And so you can upload a bunch of these one-time use keys, and those go away every time you use them. And then I should mention, there's the, I don't know if you've heard of the post-quantum crypto. These, turns out discrete log is hard for us to do right now, but if we have a quantum computer that works, then it'll be really easy, okay? So if we go back to the scenario where somebody collects all my WhatsApp messages and then wait for quantum computing to come, then they can crack all those keys really fast and get my messages. So we need to like protect now. And so this protocol becomes even more complicated because not only do they have the DSA key and the Diffie-Hellman keys to start with, they also have post-quantum crypto keys that get mixed in. So they all kind of get mixed in, and thus, when quantum computing becomes real, we're still safe. So yeah, WhatsApp and Signal care about us, I guess. Yeah. Mhm. Right. Mhm.
They are the results of the initial sequence, basically. So at some point, these both people communicated, both sides.
Yep.
To know
Right.
So it actually takes like at least probably as little as 2 busted keys to possibly know to bust all the chain completely. So it might be possible to hack all the messages by just hacking 2 keys produced by the KDFs. As KDFs, as the good about KDF, should probably share it. Sites communicate because there is no way, there's no other way for them to know to transform the data back from the encrypted stage as data.
Yeah, so I think, actually, let me go. There's a good, this one I think is a good one. So I think, yeah, so this is a good point to make. So the symmetric keychain does not have forward security or forward secrecy. So if you crack this key here, you get A2, and then you get everything else in the chain. So there's no forward security here. So between the iterations of this chain, if you crack this part right here, you get all the chains in that piece. However, once you these public keys here are ephemeral. They're just created on the fly. So as soon as you go past 2 of them, it doesn't help anymore, because as far as the public key. So between the public key ratchets, that's where we get the forward security. No, they're not. No, because when Alice generates this pair here, this is a completely random pair. Doesn't depend on. Yeah. So yeah, every time we do one of these, it's just completely random. And then once we're done using them, we throw them away. So if Alice like hoards them, then it's a problem. But yeah, so we just throw them away. So since they're each independently generated, and that's the key. I think that's the key thing, right? As you point out, since they're each independently generated, then the forward secrecy doesn't go past that point. Was there another question? Yeah. Like this one?
Well, yes.
Oh, yeah.
We have each message like its own key.
Yeah, good point. So let's go down here. So the keys, you can only change keys once the other side knows about it. So when in this case right here, A sends A2, A3, and A4, and it can't actually change. It can't actually change the public key until it gets a message from B. Because if you look at how these are changing, let me go back to the ratchet here. Yeah, you'll notice that they kind of take turns sending the public keys back and forth. Do you see that? So first Alice gets the public key from the server, and then she sends a public key to Bob. And then once Bob sends a message back, that will have a new public key in it, and the ratchet will turn. So we have to wait until we get a message from another side in order to move that ratchet. So if you were messaging a friend that responded right away to each message you sent, then each message would change the public key. But oftentimes you have a friend that's much more chatty than you are. And so you'll send a message and they'll send like 10. So those 10 messages were only generated on your friend's side. So the public key can't change until you send a message back.
Then the front guy uses another public key, it becomes a message from another.
Yeah, we distribute the new public keys with the messages that come in. Did you have a, yeah?
Don't judge me, my question is.
Sure, no, that's okay, okay, yeah. Why is it necessary to use? Yeah. Yeah, right. So the cardinal rule, like the most important rule of public key crypto is that the private key never leaves the possession of the owner. So if the private key ever leaves the possession of the owner, then it doesn't really work anymore. So that's why your private keys only stay on your machine. The only thing you get to GitHub would be your public keys, right? That's what you're asking about? Yeah. So I mean, even if it's a private repository, when you go to GitHub, you're proving, look, I'm me. I'm me. And GitHub says, oh, are you really you? I have your public key here. Prove to me that you have the private key that corresponds to it. So you exchange a signature, and then GitHub believes you and then lets you do your thing. Okay, which may be to a public repository or a private one. Okay. All right. Good. Sure.
How can we see the history of messages if each message signed by and public key, but Alice, so when she sends a message, she generates new public private. How can we see the history?
Yeah, so we can't see the history of messages. So the message history, like you're saying, like go back in time, like say, oh, I forgot about those messages. Let me get them back. Yeah, so you can't. Yeah, because of our perfect forward secrecy, right? So we can't do that. So that's why WhatsApp says back up your messages. So your client can keep a copy of the message, right? And then you can do the message history there. But yeah, you can't go backwards. Locally. Uh-huh. Yeah. Yeah, WhatsApp is kind of cool. Actually, when Facebook bought WhatsApp, there were only, it was like $5 billion. They had like 30 employees or something. Because the thing about WhatsApp is they don't really store that many messages. Like any messages they store, they're just messages that they're trying to send to somebody else. And as soon as it gets to the destination, the message goes away because they don't store any messages. All they store is the mapping of public keys to phone numbers, which is just a little bit of storage. And the only time that the clients need to access that storage is when they first talk to the other side, when they're first establishing that connection. So as far as the amount of work that the WhatsApp server does, very little, and they need very little storage. So it's kind of a really cool economical setup for them. Yeah, as opposed to like Gmail, for example, where they need like gigabytes of storage for all of us because all our emails are there. All right, yeah. Mm-hmm. Yeah, you know, I'm not that familiar with Telegram. Yeah, they just store it on the server. Yeah, a lot of times they store it in clear text, which is the problem. So when you talk to the server, it's encrypted. So like it's protected from the internet. But if an attacker breaks into the server, then they can get access to all the messages. And this was one of the big scandals that happened in the US when a few years ago when Edward Snowden found out, exposed that the US was like infiltrating tech companies and like mining their data. So that was, yeah. So it's problematic. So double ratchet is safe because the server doesn't know. The server never sees the actual messages. Now there is the one hole in double ratchet is this hole right here. Whoops. Yeah. So let's see if I can go. Yeah, it's this hole right here. So it turns out phone numbers aren't the greatest thing to authenticate with. Right? You change your phone number, you forget about the old one, somebody clones your SIM card, somebody steals your SIM card. So yeah, this is a bit of a hole, the whole thing. But apart from that, it's very good. All right, so we should probably wrap up. I'm happy to hang around as long as you'd like. So I'm happy to talk to you. I do have a project related to this that I would love your help with. And also, if any of you are in the programming team, I'm the coach of the programming team in SJSU. I would love to see how it's working here. So, all right. So I'll see you next week. Thank you, everyone.